Hi there. We are now solidly into the last chapter, which is focused on chi-square tests. You'll be happy to know that these are the easiest tests or easiest hypothesis tests that you will learn over the course of Introduction to Psychology or Introduction to Statistics in Psychology. Um, they tell us the least, but they are useful in certain circumstances and they are fairly easy. So let's kind of take a look at when and why we would use a chi-square test. So whenever we are considering a inferential statistic, we typically are looking at testing hypotheses that um, share several assumptions about the parameters. So remember, parameter is values that describe the population. With parametric tests, which are the tests that we have basically dealt with, t-tests, ANOVA, Pearson-R correlation are all parametric tests, and they share specific assumptions, typically related to normal distributions, homogeneity of variance, and quantitative data, so numerical scores for each individual, so that quantitative data. We don't always have that, though, when we are conducting research. So sometimes we actually need what is called a non-parametric test. So a parametric test is all of the tests that we've done so far. The independent T's, all three of those independent T's, any of the ANOVAs, and the Pearson-R, because they meet those assumptions about normality, homogeneity, variance, uh, um, and like for Pearson-R, homoscedasticity. So those are assumptions that are need to be met. And the key is the dependent variable is measured quantitatively. But non-parametric tests typically can be used when that research does not kind of conform to what we would need for a parametric test, either through the research design or maybe through limitation of a sample size, and you need to condense things into kind of the type of assessment that does not fall into alignment with those natural assumptions that you would get from parametric tests. So let's kind of look at what is necessary for parametric tests versus non-parametric tests. So if you recall back way back in chapter 1, we talked about measurement scales or scales of measurement. For parametric tests, the dependent variable has to be measured using either an interval or ratio scale. So you need to have quantitative data. So for example, intelligence, it can be any value, but the 0 point does not mean that there's an absence of something. The 0 is just a placeholder. Or a ratio scale like weight and age, there is an actual 0. It's not just a placeholder. It starts at 0. Like any kind of physiological measure starts at 0. So both of these are quantitative data that can adhere to parametric tests and the ability to maintain the assumptions necessary for inferential testing using those parametric tests. Often, though, sometimes we fall into where we have tests that require a non-parametric test because we either have nominal or ordinal data. So data that's just organized into categories. So like Republican, Democrat, Independent. They're just categories of individuals. Or ordinal data where there's a ranking, like for this, like low ability, medium ability, high ability. There's kind of a subjective difference, but it's not, you can't subtract high ability and low ability and find a difference. There is a subjective difference. These types of this type of data would be really what we would consider as, I'm sorry, I had a little pop-up. This type of data would make us kind of force us into using a non-parametric test, which chi-square tests are considered non-parametric tests. So chi-square, there's a couple of different types of chi-square tests, but they're what is called distribution-free tests because they don't have a normal distribution, and we can't make very many assumptions about the population. So previously, our hypotheses were stated in the form of what we would see in the population parameter. So if we have a sample and we see a significant change in that sample due to some treatment, we can assume that we would see the same change in the population parameter. But we often can't do that necessarily with chi-square. We can test hypotheses, but we can't, there's not a lot of assumptions or inferences that we can make about the population, and we can't maintain the assumptions like normality, those types of things, because they're distribution-free tests. Because the data does not align with that bell-shaped curve. It's just categories. So typically nominal or ordinal scales are used for this type of data. And the data that we have is just based on frequencies. So how many people fall into this category, or how many people fall into this other category. That's all that the data is basically saying. So the first chi-square test that we're going to learn is the goodness of fit. So you're going to learn two different hypothesis tests using non-parametric, and that's specifically the chi-square goodness of fit, and then we're going to look at chi-square test for independence. So first and foremost, let's look at the chi-square goodness of fit. So all this does is test hypotheses about the frequency across categories for a single variable. So it could be like if you have a preference between dogs or cats, the one variable is pet, type of pet. And then you have two categories within that variable. So the one variable is type of pet. You're just looking at how many people prefer dogs, how many people prefer cats. So that one single variable and just frequencies are counted. Really, all this is saying is there's no preference among categories if you're talking about the null hypothesis, because again, we're testing the null, we're actually trying to disprove the null. And the null would be that there is no preference across categories, or no difference across the categories, or no um, uh, proportion is greater in either of the categories or any of the categories. And it can be more than two categories within a variable. So here's some notations that you're going to learn. Chi-square is that Greek letter chi and then squared. That is the notation for the test statistic. So it'd be chi-square is your obtained test statistic. You'll see the notation F subtext 0 or O, and that's the observed frequencies. So that's the data you collect, how many people fall into each category. And then there is F of E, which is the expected frequency. And this is based on your null hypothesis. So this is why I say this is the easiest test, because no longer do you have sums of squares, because we don't have that normal distribution. We don't have variance. We're just looking at expected frequencies versus observed frequencies. So if you'll notice, it's the summation of f of O minus f of E squared divided by f of E. So basically, you just subtract the expected frequency from its observed frequency, square that difference, divide it by the expected frequency, and then add to the next one, and you'll see what this looks like. So for each basically category, you're going to have a little fraction, chi-square fraction. So here's an example. So let's just look at difference in eye colors. So we have eye colors, 4 categories. Eye color is our one variable. So eye color is basically our independent variable, let's say. But it's not an independent variable. We don't have control over it. So it's a quasi-independent variable. So that one variable has 4 categories. You can have blue eyes, brown eyes, green eyes, or other. Okay. Maybe other is rainbow. Who knows? All these are these right here, the 12, 21, 3, and 4. These are our observed frequencies, F of O. So 4 people had other, probably had hazel or something, or gray eyes. 3 people had green eyes, 21 people had brown eyes, 12 people had blue eyes. So our combined sample size is 40 for the entire study. So we have our observed frequencies. Let's explain how we would get our expected frequencies. So first we need to know what our hypothesis is. So in this scenario, our alternative hypothesis is that the proportion of eye color will be significantly different across 4 categories. All it's saying there's going to be a difference across. It doesn't say that there's, green eyes are going to have the most. Sometimes there will be a specific hypothesis, like in the population, years before we had noticed that 60% of the people have brown eyes. Well, then your expected frequency for the brown eyes would be 60%, and the rest would be split up equally between the others. But for this, it's just everything, they're going to be the same, basically. All 4 of those categories are going to be the same. So if we have 40 participants, and we have 4 categories, we're going to start like going through the steps. So we stated the hypotheses. Okay, now we need to set our criteria. Okay, again, you have a whole new table. It's at the back of your textbook. It's the chi-square table. So it's after your Pearson R, and it's table A.6, and it's called the chi-square critical values table. And now instead of using sample size, which was 40, if you recall, we're no longer using sample size for degrees of freedom. What we're using is C, or -1, which is basically C is the number of categories, is what that is. Categories -1. So in this case, we have 4 categories, -1, our degrees of freedom is 3. If you look in here, there's a 0.05, there's 0.01. If we look up 3 and we're using 0.05, you'll see our critical value is 7.815 using that chi-square critical values table. And that is table A.6 in that textbook. So now we have the criteria. Even though these are distribution-free tests, we're still finding the criteria kind of in the same way. And chi-square is similar to ANOVA in the sense that it's always going to be positive. So we're just using this distribution as an example. It isn't a normal distribution, but that's how the criteria is set up. So our critical value equals 7.815. Any test statistic that falls beyond that is significant. So here's where we would have significance. Out here is no significance, just like it was in the past. It's going to be the same thing, except for we're just dealing with non-parametric tests. So now to get our observed frequencies. So we had 40 people in the entire study. We need to come up with our observed and our expected frequencies, but we need to be careful. When we are collecting data, we need to make sure that we're meeting certain assumptions. One is being that are certain requirements, not assumptions, but requirements, that each individual is only counted once. And so for your observed frequencies, these are just how many people fell into this category, like into the blue category. 12 people fell into the blue. Let's say you have someone that says, well, I'm kind of blue eye and green eye. I'm a little bit of both, so I put me half in blue and half in green. You can't do that. You have to choose. So probably if somebody has like a mixed where they're bluish green, then they'd have to go in the other category. You can't go half and half. Only one person per category, one time in a category. With the observed frequencies, these are always whole numbers. So F of O is always whole numbers. That's because they can only be one observation per category for each person, or like one person can only be in one category with one observation. They can't split their observations. So that's our observed frequencies. But to get our expected frequencies, it's going to depend upon the alternative hypothesis and the null hypothesis. So our null hypothesis for this is basically there's not going to be a difference in the frequency of eye color. So there's not going to be a difference. So that just basically means that if there isn't a significant difference, we would see equal amounts across the four categories. So we can do this a couple of different ways. I kind of always go, okay, the sample size, right? N, right? You have four categories, right? And you have a total of 40 participants. I would just divide the total number of participants by how many categories you have, which is the same thing as 1/4 times 40, because you need to find out, okay, what's the expected frequencies for those with blue eyes? 1/4, 1/4 of the sample size would go into that category. So 40 divided by 4 is 10, or 1/4 times 40 is 10. So expected frequency of 10 for each of these cells. Now, if for some reason I said, okay, well, 60 in the regular population, it was said that 60% of the people have brown eyes. Well, in that case, then I would be doing 0.60, 60% of 40 would go into the brown eye category, is what I would do. And so, and once you would get that, then you would put that number in there. Let me get my calculator, because I don't do anything by head, like in my head, because it never works out that way very well, because you're trying to do too many things at once. That's why I always tell students, don't calculate in your head. So 0.60 times 40, because that'd be 60%, that would be 24 people. Well, then we would take 24 from 40, and the remainder would be split evenly into the other three categories. This is just if for some reason your hypothesis had some prediction that it's comparing to. But in this case, we're just looking at no difference. And I more than likely on any exam, I would not give you one where there is a prediction where you have to split them unevenly. But for the expected frequencies, you can have decimals. You cannot on the observed frequencies, but you can have decimals for the expected frequencies, okay? So once you get those expected frequencies and your observed frequencies, then you can start calculating your chi-square. So if you'll notice, you're going to have, for this in particular, basically four little chi-square fractions. So for cell, the first category, blue, our observed frequency is 12. So here's 12 minus 10, that expected frequency, because remember it's observed minus expected. You take that squared number and divide by 10. So this little fraction right here ends up equaling 0.4. And then, because again, this summation is here, you're going to add that to this fraction, which is related to the second category. And then vice versa. So this one goes, when you do that fraction, is 12.1. This is for our green category, and that is related to 4.9. And this is related to our other category, right? And that is 3.6. So once we add all those together, our chi-square test statistic is 21. Really quick and easy, right? That's the easiest part. The part that I see students making the biggest mistake on is not putting parentheses around the numerator. If you don't put parentheses around that numerator, is what happens is you take your frequency of your expected squared, divide it by its expected, and then subtract that from the observed, which is a different calculation than that numerator as a whole divided by the expected frequency. So make sure that you're doing those order of operations carefully. So here's that conclusion. This is as simple as it gets. The goodness of fit doesn't even have an effect size because you can look at the data and basically say what's happening. So in this case, I said the proportion for eye color showed there was a significant difference or there was a difference in eye color across 4 categories, would have been just fine, as chi-square. And this is your degrees of freedom. And this is included. This is your sample size. Okay, so those need to be included. Degrees of freedom, comma, sample size. And then your obtained test statistic, P is less than 0.05 because this was significant. So whenever it's significant, P is less than the alpha. And then that's the end of the sentence. And then I would just say what's happening. Brown eyes was observed most and green eyes the least. That was really the simplest way to explain it. What you see the most, what you see the least overall. So done and done with chi-square goodness of fit. Now we can go into the chi-square test for independence. The chi-square test for independence is used when we actually have 2 variables and we're looking for a relationship, but we can't use Pearson R because the 2 variables are categorical. So if you look at this, it's still frequencies within categories. So for this specifically, we have the number of children. If the categories we have are 2 or less children or more than 2 children, and these are just frequencies, but we're also looking at a second variable. So we have number of children is our first variable, but education is our second variable. So it should probably have over here like education. Okay, is kind of like that second overall variable. So, and we have 2 categories here, college education or high school education only. And so these numbers are frequencies. 53 people said they had 2 or less children and they were also college educated. 22 people were college educated and had more than 2 children. High school education only, 37 people had 2 or less children, but 38 people had more than 2 children and a high school education. So all it's looking for is the frequencies and that relationship between the 2 variables is what it's looking for. So it is another form of a test for a relationship, but it's used when you have those categorical variables. So here's what our alternative hypothesis would look like. Basically, the number of siblings is significantly related to parents' college education. Basically, with a test for independence, if the null is true, which means there's nothing going on, that means the variables are independent and there's no predictable relationship between the 2 of them. That's really what test for independence means. In this case, we're going to say the number of siblings is related to parents' college education for our alternative hypothesis. For the criteria for the test for independence, you have to account for the fact that there's 2 variables. So basically, I look at, R minus 1 is R is the number of rows and C is the number of columns. Okay. So rows and columns. So basically, you're going to take your rows minus 1. In this case, we have 2 rows. Minus 1 is 1. And then we have columns minus 1. We have 2 columns. So 2 minus 1 is 1. And we multiply those 2 together. So it's basically, in this case, degrees of freedom is 1 times 1 once we do that math. You can have more than a 2 by 2. You can have a 2 by 3, you can have a 3 by 5, a 4 by 7, but in this case, you have a 2 by 2. So your degrees of freedom is 1. And then you would use your chi-square table, critical values table. So if we use 0.05 and we have a degrees of freedom of 1, our critical value is 3.84 is what that is. So let's take a look at how we get our expected frequencies. So these frequencies here, the ones that you already see, like 53, 37, 22, and 38, those are our expected or observed frequencies. So these ones are the observed frequencies for the 4 different cells. but we need to come up with our expected frequencies. So to do that, we have to get our kind of our row marginals and our column marginals. So what that means is basically add up each row and then add up each row sideways and add up each column. So if I looked at 53, which was our observed frequency, and 37, the other observed frequency, if I added those together, that would be 90, and that would be a column marginal or column total. Again, then 22 plus 38, those were our observed frequencies, add those up, and then we have our column marginal for the second one. Then we do it the same for the rows. So 53 plus 22 is 75 for the row marginal. 37 plus 38 is 75 for that row marginal. Now, either way, if you add the row marginal or the column marginal, it should equal 150. And that 150 is your total sample size for the whole study. How many people participated in that entire study? So once you get those columns and row marginals or totals, you can get your expected frequencies. So to get your expected frequency, you're going to multiply your frequency column times your frequency row, which means basically your column marginal times your frequency marginal for that category. So if we were looking, and I usually number my cells, so for cell 1, for this cell, I'm not going to do anything with 53. Is what I'm going to do is look, okay, what is my total in that row? The total in that row is 75. And then the total in that row in that column for 53 is 90. So for that, if you look at for cell 1, it's 90 times 75 divided by the total number of participants, which is 45. So 45 is our expected frequency for this. So I'm going to put that here, F of E. And 53 is our observed frequency. And that is supposed to be an F, and that's supposed to be an E. So same thing, if you were looking at this, the second cell here, I'm going to look down here at 60 times 75, because you're just lining it up, and then divided by 150. So cell 2, that's our expected frequency, F of E. So you do that for each cell. For this, for the cell with 37 in it, it's 90 times 75 again. And for the fourth one, it's 60 times 75 divided by 150. Don't forget to divide by 150 to get your expected frequencies. So you have to do that for each cell. So you're going to get an expected frequency for each cell. Once you have those, that's the only new thing that you really have to do for this is you can start calculating those. So you're going to have, again, four little chi-square calculations is what you'll have. So it's the same equation as the goodness of fit. The only difference is that calculation of the expected frequencies. So that's that column marginal times the row marginal divided by the total N. Same equation though. So as you'll see, now here's my observed frequency, 53. My expected frequency for that first cell is 45. So here's my first little fraction. So my first chi-square for this cell is right here. And then for the second cell, I have basically, here's my other little fraction that I'm adding together. And then the third cell, and that's why I usually number the cells right here. That's my little fraction. And the fourth cell is the 38 minus 30. And that's its little fraction that I'm adding them up. So then once you add up those totals, we end up with an obtained test statistic of 7.07. So There is actually an effect size with chi-square test for independence. There's actually an effect size. It's going to depend on whether you have how big your matrix is. Basically meaning, do you have a 2 by 2 or like a 2 by 3 or a 3 by 5, etc. So if you have a 2 by 2 matrix, you're going to use what's called the phi coefficient. That is a measure of the strength of the relationship. And so the phi coefficient is chi-squared, that's your obtained test statistic, divided by n, and then take the square root. This is for a 2 by 2. So we just did a 2 by 2, so we're going to use phi coefficient for this one that we just did. If you have larger than a 2 by 2, you're going to use Kramer's V. It's inappropriate to use a phi coefficient on anything bigger than a 2 by 3 or larger. You have to use Kramer's V. So if you have a 2 by 3, you're still going to have the same value for V as if you had phi coefficient, because you're multiplying the sample size by the lowest degrees of freedom. So remember, you have row -1 or columns -1. Whichever one of those is smaller is what you're going to multiply n by. So if it's a 2 by 3, you would just be multiplying V1, and it would really be the same calculation as phi coefficient, but you shouldn't report a phi coefficient for a 2 by 3 or larger. You would report a Kramer's V, which again is that strength of the relationship between those two variables. Again, this is your obtained test statistic. Okay, so let's take a look at how that looks really quick. Oh, I didn't even give you results on that one. So let's take a look at this. Let's go back. If we have 7.07, okay, and remember we had 150. So we're going to use phi. It would be 7.07 divided by 150 under that square root. So we'd have 7.07 divided by 150, okay? Take the square root, and we should be getting a phi coefficient equaling 0.22. It's 0.21710, but I rounded it to 0.22. If you'll notice, our chi-square test statistic is 7.07. Our original critical value was 3.84. So let's go back and let's take a look at that. So here we have our boundary is 3.84. Anything that falls over here is significant. So that's that critical value. 7.07 would fall somewhere over here. So it would be significant. So if we took a look at this, so there we would basically say there is a significant relationship between college education and number of children. So I'm going to kind of write this here. There is a significant, and I'm going to abbreviate it, relationship between education I totally missed a step with the results, but that's okay. And number of children as chi-square, and we're going to put parentheses. If you remember, the degrees of freedom was 1, n equals 150. The test statistic was 7.07. P is less than 0.05, and chi-square is always one tell with that phi coefficient, if you recall, was 0.22. Equals 0.22. And that's a very sloppy phi, but it is a phi coefficient. That's all we would say. There is a significant relationship between education and number of children. Give the chi-square, the test statistic, how P is related to alpha, and your effect size, and you're all done. So just as a kind of wrap things up, there are actually some restrictions of chi-square tests. So obviously we have to have those independence of observations, meaning each frequency is generated by a different individual. You can't have one individual in more than one cell, basically. And with chi-square, our expected frequencies cannot be less than 5. So when you calculate your expected frequencies, every cell has to have 5 or more for us to be able to conduct a chi-square test. So hopefully that kind of helps clarify. That's the limitation of those assumptions. So there are times when chi-square is necessary. So basically chi-square and Pearson can look at those relationships, which is beneficial. Sometimes we'll use chi-square for a t-test or ANOVA when there's frequencies with the categories, and we have to exchange the values for frequencies. So maybe you you accidentally ask someone for a category like what was your last exam score? And their answer is like 80 to 90%. Well, that's not an exact number. So now you have to kind of break everything down to fit into those categories. And then there's the frequencies of those categories. So that could only be when that is required. Or you'll use chi-square tests if the assumptions of your ANOVA or t-tests or correlation are not met. And you feel like, well, this is going to invalidate my results. So I'm going to switch this to a non-parametric test so that I can actually test this hypothesis. So there are some applications of chi-square tests that are necessary. The least used research for social behavioral sciences. Often chi-square is used for things like marketing, like what brand of soda do you like best? Those types of things. And then it's just frequencies. That's when we see chi-square tests used the most is for marketing. So hopefully that helped and can wrap things up. Please go in and find the other practice activities. And I have some examples of going through calculations of chi-square and reporting the results. So utilize those resources.